Welcome to this Eisenstadt Chair lecture by Éva Tardos. Éva Tardos is a Jacob Gould Schurman Professor of Computer Science at Cornell. She has earned several awards, too many to list here. Donc, bienvenue tout le monde au CRM pour la conférence de la chaire Eisenstadt de Éva Tardos. Éva Tardos est la Jacob Gould Schurman Professor of Computer Science de Cornell. Aujourd'hui, elle va faire son deuxième exposé dans le cadre de la chaire Eisenstadt. Le premier était en 2020 et il a été retardé, comme vous le savez. C'est-à-dire le deuxième a été retardé. Éva Tardos earned so many prizes that it is impossible for me to list them here. Let me mention perhaps that she is a fellow of the AMS since 2013 and that she won the Gould Prize in 2012. Elle a donné la lecture Sonia Kovalevskaya en 2018. And today we have the pleasure of having her here at the CRM, where she will lecture on stability and learning in strategic queuing systems. The floor is yours. Thank you very much.
So thank you very much. And I'm sorry I can't be there in person. I guess the Zoom thing is a, mediocre backup to the in-person version of life. I do appreciate all of you who are willing to keep your videos on. It's like really somehow nicer to talk to humans than to talk to boxes of pictures. So if you can and you're willing to turn your camera on, that would be nice. So indeed, I'm planning to talk about stability in learning in queuing systems. And before I start talking about queuing systems, I want to remind you, hopefully I can do this, yes. I want to remind you of sort of the bigger agenda that I have been working on and that I gave a lecture by now, almost 2 years ago, or maybe 2 years ago, as the first of these lectures, and then tell you how what I'm talking about now fits into the bigger agenda. As usual, if there are any questions, feel free to either unmute yourself and just chime in, or I'll do my best to keep the chat window open in case you type something in chat, but if one of you could warn me if I mess this up and there is a question in the chat window and I'm not noticing it, that would be very appreciated. So again, what I want to talk about is stability and learning in queuing system. And I guess stability is maybe refers to that this is game theory, and learning is that sort of was the message that I think I tried to do in my previous lecture, that learning is a very reasonable and very practical model of how to model or how players might participate in games. So in the, oops, this is not as easy as I thought. Okay, in the games and game theory part, what I have been working on for years and I'm most focused on is consider some game that models some real life situation and ask the question of, as self-interested, selfish participants participate in such a game, how bad or how much they damage the social welfare by not having a blind dictator tell them what to do. So I guess the standard measure for this is what's called the price of energy, which is a worst case gap between the social welfare at a, say, Nash Equilibrium, so a selfish outcome, compared to a social optimum. And I guess a game that is not exactly the game I'm going to focus on today, but something, a simpler version of this game that it's nice to start with always is traffic routing, where you can think of traffic either as car traffic or packet traffic. And I guess the thinking of this as game theory, one would say that, if there's congestion around the route or around the intersection, that of course causes delays. Cars or packets are selfish, which in the case of packets, it's the routers that decide what they do, but similarly, they're trying to follow a shortest path. And what you're asking is, what's the overall costs, like say average delay or total delay of all the packets or cars, which of course depends on the congestion. So the bigger the congestion, the slower everything gets. And how did that compare to an optimally designed traffic pattern? The sort of one of the early results, definitely early results of mine in this area, is the following, which is sort of going to be my role model for today, is saying that in any network, as long as delay is a continuous, non-decreasing function of the amount of traffic, which I think is a pretty reasonable assumption, if a cost of a selfish outcome is no worse than a centrally designed optimum traffic pattern that has to carry twice as much traffic. So what in English this says that if you want to let people just selfishly drive whichever day or send their packets on the shortest path, you can make this possible as long as you design your network with twice as much capacity. And this is a very sort of actionable design question, and this is the kind of question that I'm going to ask in a different context. How much extra resources do we need to offer a system if we want to guarantee good outcome? Price of energy is a related measure. It's not quite the same thing. It says that you literally compare the selfish outcome to the Nash equilibrium, that is without this inflation of a factor of 2 of resources. I guess at the moment I'm going to stay with the how much extra resources do I have to offer style question. So this is what I mean in analyzing games and selfish outcome, selfish behavior, and I'll come back to more formal definitions in a second. Before I do that, I keep having trouble here. I guess I should come back to the learning part. So the kind of games I want to focus on, and packet routing or car traffic is definitely one of those games, is things that are not a single interaction. So I'm not talking about, when the government wants to sell off, bandwidth areas for use. That's a one time in your lifetime kind of interaction. It's different than traffic routing, which happens every millisecond or every morning. I want to think of these games that are repeated games where participants participate over and over again. And I guess this mode as a repeated interaction. So, on this picture, I guess you should view that moment 1, all the players do something happens, and over time, many things happen to them. It is a very simple assumption that they're going to do some sort of learning, that they're going to try to learn what is good behavior. And one particular model of learning, mathematical model of learning I was advocating for last time, is the assumption that they satisfy the no regret condition. This is what the no regret condition says, that the cost that the players incurred should be not much bigger than the best fixed action with hindsight. So I guess what that's trying to say in English is you drive on some highway and you keep trying out what are good highways. If there is a single highway that gets you to work and it's very efficient every morning, you might be able to do better. It might be that, as it turns out, Tuesdays, some other road is better, and Wednesdays, something else is better, and you can figure this out. But if there's a single good solution, then a decent learning algorithm should wake up to this fact and learn it. So that's the no regret condition. And there are lots of sort of nice arguments of why the no, assuming that every learner is satisfying the no regret condition is a decent assumption, or at least a reasonable assumption. So I repeated on this slide what the assumption was. Again, the cost that the player I incurs over time is not much worse than the cost of a single best action with hindsight. The not much worse is the, over time t less than linearly growing with time t. Of course, as they're learning, they might initially make mistakes. So I need a little bit of an error term, and that's what this term here represents. And I guess my two sort of general pitches for this as a behavioral assumption. There are simple, effective algorithms that actually achieve this. I don't want to spend a lot of time on this, but in very different contexts, in auctions, we do have data for behavior, at least the bigger bidders that clearly are using learning algorithms, that they do satisfy this assumption. Humanly, it seems like a very reasonable assumption. And maybe the last point is a lot of early work in this area just assumed that these players will reach a stable solution, a Nash equilibrium of the one-shot game and repeat it over and over again. I guess that's what the picture on the bottom appears to represent, like they're learning initially and then they reach a stable solution and just repeat it forever and ever. And then they analyze ignoring the upfront learning part, they analyze what happens at this Nash equilibrium. The assumption that everyone is a no-regret, satisfies the no-regret condition is a weaker assumption than this. If they reach the Nash equilibrium, then by definition, they satisfy the no-regret assumption. The only part they have regret for is this initial part. No regret is exactly the Nash equilibrium condition for this part here. So it's a weaker assumption. It does seem to be satisfied by data, and it's doable algorithmically with no assumptions, and even easier if you make assumptions about the data. The biggest pitch of what I told you last time, and with this slide, I will end in sort of the summary of what is, I don't know, 20 years of research at this point, and something I talked about a lot about my last lecture, is that there's a lot of beautiful work on generally analyzing pies of energy, I guess starting with Koutsoupis and Papadimitriou, who proposed this in the 99 paper, comparing Nash to the social optimum. These are some of my favorite results here. I guess I'm heavily favoring myself here. But most importantly, almost all of them turns out that the same proof actually proves that the same band applies under the no regret assumption. So we don't have to assume that the players magically found the Nash equilibrium. It's enough to assume that they're no regret learners, or at least satisfy the no regret condition. Again, I can defend the no regret condition, and then the same bands apply, so we can count on the decent or reasonable social welfare. And then, maybe you conclude here, and this is something we're going to start questioning in a bit. Wait, so we should conclude that we should actually convince people to do no regret learning. No regret is the right form of learning, because look at the nice consequences we have here. So this was my however many minutes, couple of minutes summary of something I did for a longish time in the last lecture, and actually summarizing, as you can see here, more than 20 years of history of what happened in this area. Again, a lot of the initial work was just analyzing price of energy, and then about 12 or how many years ago, maybe 14 at this point, we started to think about this learning outcome, and more results extended to learning outcomes, even under some interesting assumptions. So this was a whirlwind tour of 20 years. Here is the new thing I want to point out, which maybe after such an introduction, you're not surprised to hear that I'm going to start by, wait, something was wrong with all this. Let's actually think about some details here that actually matter. So if I look at the details of the proofs, and I admit, assuming that all of you well remember a lecture that happened 2 years ago is not a reasonable assumption, but this is a fact. But the assumption behind the learning outcome is that that the new game, there's a new game showing up. Every iteration is a new copy of the same game. That is, no carryover effect between rounds, other than, of course, the learners learn what's right. And I guess one question I should ask, or question I'm going to start by asking, wait, is this a reasonable assumption? That is, can we assume that other than what the people learned, there is no physical carryover effect from round to round as they're trying to learn? And I guess going back to my traffic routing example, I think the correct answer is sometimes yes and sometimes no. And many examples when the answer is no, we might want to know, okay, how to think about those games. So I would say that the answer on morning rush hour is definitely yes. No matter how bad traffic jam you participated in on Monday morning, those guys are gone on Tuesday morning. They're not still sitting on the road. You can start all over again and think about which way to drive. And you might meet the same cars because they too have to go to work on Tuesday morning, but it's not like the traffic jam from Monday morning stayed on the road all the way to Tuesday morning. This is in contrast if I look at either car traffic second by second, but certainly packet traffic second by second. If in 1 second you observe that some packet routing or some router is over congested, a millisecond or even a second later, it's the very same packets that are still there. Or put it another way, admitting that the way technically this works, when packet traffic gets over congested, then these packets get dropped and then the sender has to resend it. But the congestion itself in 1 second is causing the congestion of the next second. It's not learning, it's not like you're doing the same thing. It's literally the same packets because they didn't go through, they're trying to still go through, and that causes the congestion. So the question I want to ask today, what can we do, or how can we think of games that are stateful in this sense when there's a dependence between games in each round? And there are 2 questions I want to ask and provide at least hints of answers, or however much we know about the answers right now. How much extra capacity ensures good system performance despite selfish users? So this is the question I showed you with the traffic routing paper that Tim Rovgard I had early. Says that twice as much capacity is enough in the classical packet routing. And I want to say, if everyone is a learner, how much extra capacity would assure good system performance despite everyone selfishly learning? But I also want to ask, is no regret learning the right way to do learning? Is that the right condition in case of a stateful system? And maybe to give the punchline away, the answer between the 2 questions is going to be yes or no. So yes, a bit of extra system capacity can ensure good performance if they're learning, but no regret learning does not appear to be the right way to learn. And I want to show both in the next, the rest of the talk. So let's actually start with the very, very simple model that I want to use to illustrate this. And I admit, while I'm thinking packet routing as the sort of basic thing I want to try to model here, this is a super simplified model of packet routing. So I guess my plan for the talk is step number 1, I'm going to tell you what the model is that we're using. Definitely want to give you a chance to ask questions as I describe the model, just to make sure we're all on the same page, and then give you some ideas of what we can prove and some ideas of why those might be true. So instead of long paths, I'm going to just think of packets arrive and their servers, and there will be these queues, which are the blue squares on my screen, are trying to send the packets to the servers to get it served. To make the model concrete, maybe every queue will have a new packet arrive as a Bernoulli process with some rate lambda I, and every server is capable of serving a packet with some probability uj. It does the server's capacity or ability to serve. Most of my examples of servers will be perfect. They can serve everything all the time, but the results extend if their servers are not perfect and has this uj probability of actually serving something. Every iteration, and this is modeling real packet routing, every queue can take one of their packets and send it to one of the servers. That is, the way queues work, there is a limitation of what they can process, and what they can do is take one packet and decide which server to send it to and send it to that server. Maybe not surprisingly, I'm going to assume that the servers can only serve one thing at a time. So what will happen is, and in the general model, that every server that got 2 packets, like, or multiple packets like this one, has to select one of the packets and serve that one, or try to serve that one. If it succeeds, it's cool. If it fails, then, or if it was not the selected packet, then it's going to, I guess, send the packet back to the server, or actually be more realistic of how packet routing works. What I assume is drops the packet and they're going to have to get resent. So again, the assumption is that every queue can only send to one server at a time. This is a process limitation on the queues, and every server can only serve one packet at a time, obvious packet limitation on the servers. Both of these assumptions are very realistic. The place I'm cheating or simplifying my life is that the actual servers usually have a bit of a buffer. They can buffer 2 or 3 packets before they start dropping them. We didn't model the buffers, so we're assuming that as soon as they're not serving something, they're just sending it back. There is an important part of the model I didn't yet talk about, is when you get multiple packets, which one you're going to serve. And the model that we ended up using is that, assuming that the packets are timestamped, and they're going to serve the oldest packet. And if people ask questions, I'm happy to elaborate of why timestamping and the oldest packet is maybe the right assumption here. So again, that's the model. I can remind you of the question. If I take this system and then somehow this number of servers, or the capacity, or the ability, the mu-j's, the probabilities that the servers can work, is in some way the capacity of this system. And what we're going to ask is, how much extra capacity do I have to give a system if I'm not coordinating the servers? Before I again talk about any results, let's actually start with some super simple examples. 1 queue, 1 server. There is no learning, no nothing, because there's only 1 server to send to. This queue, if it has a packet, it's going to send it to the 1 server. And presumably this is sort of queuing theory 101 or queuing theory 001 or something. Hopefully you are familiar with this. Obviously, if the arrival rate lambda is below the service rate of the server, then the queues going to remain bounded in expectation. This is a biased walk on a random half line with probability mu, we go up 1, probability, sorry, mu, we go up, lambda, we go up 1, with probability mu, we go down 1. And if mu is bigger than lambda, then we're going to stay close to the origin in expectation. If mu equals lambda, then there is some more tight-knit results, which I'm going to maybe be ignoring for, like, not be precise for this paper, but obviously, or this for this talk, mu is big, lambda is bigger than mu, then you don't have any hope. Packets are arriving too fast and you can't serve them. So obviously the queue behind the server will just grow indefinitely, and there's nothing you can do about it. So that's the sort of simplest case. The next simplest case, which is something that we learned from a paper with Krishnasamy, Sen, Johari, and Sakotai, which was in NIPS 16, so by now 5 years ago. They actually were thinking of 1 queue and many servers, and they used the same model. This one queue is using a learning algorithm to figure out where to send its packets. And I guess what they found, so what does this queue really want? He wants to figure out which one is the best server. Given that he can only send to 1 server at a time, the best thing he knows how to do is send to the best server. He just needs to figure out which one that is. That's a standard Bayesian multi-arm bandit problem. And what they're asking is not how long it will take him to figure it out, because that we know from multi-arm bandit, but how long will the queue be before he figured it out? Which I think is a nice question, and they offer some elegant answers to this. And what we're doing here is exactly this model, except in addition to figuring out what are the good servers, these queues, because there are many of them, will compete with each other. So we all send to the best server, that's not the answer, because then we're too much competing. We need to distribute our packets to the different servers if we want to succeed. And my question is, how do learning algorithms accomplish this, or do learning algorithms accomplish this? So I'm going to start talking about what can be done in this model. So if there are questions about what the model is, then this is a good moment to ask. I hope I can take silence to mean that everyone is.
Actually, I do have one question. So I'm trying to understand what the queues represent. Are they like, is a single queue one agent?
It's an agent in this game. If you want to think about packet routing, then it's one of the queues sending to, like, one step in the routing business. But in the game, every queue is an agent who's trying to serve, like he's getting packets, and his goal is to get his packets served as fast as possible. So he's
perfect.
sending.
That clears it up. Yeah, thank you.
Good. So before I can talk about what happens if they're learning, I probably should answer the question of what happens if we coordinate. That is, what's my baseline measure? How much capacity do I need? And the answer is not very surprising, and also not hard to prove, though I definitely won't go into the details of that. If I want to think of a baseline measure, then of course I'm assuming like everyone knows everything, so full knowledge. So I might assume, for notational convenience, that everything is ordered. That is, the first queues have higher arrival rates, and the first servers are better. And again, this is just a baseline measure here. What would I do if I know everything and I fully coordinate? And we claim that the necessary and sufficient condition is that for every integer k, if I take the first k queues, so say the top two queues, and look at this total arrival rate, the sum of the arrival rates between those two queues. Remember, every queue can send to one server. So if I'm thinking about two queues, they can use at most two servers. So then the top two servers should have enough capacity to accommodate it. So maybe actually let's back off to k equals 1. The highest arrival rate queue should have arrival rate less than the highest service rate server. That was our one queue, one server example, or that actually was also the NeurIP 16 paper's point. It needs to find the best server, and that should have enough service rate. If for k equals 2 means the top two queues that get the most packets, the top two servers should be able to do this, because two queues can only use two servers, and top three queues, the top three servers should have enough capacity, and so on for every k. It's very natural that this is a necessary condition, and it's not very hard to prove that it's actually sufficient.
Excuse me, I have a naive question.
Sure.
Why can each queue send to only one server?
So that's an assumption.
Okay.
And that's how packet routing works in the, say, the internet. Okay. That's an assumption we are making. Thank you. It's interesting what happens in system when that's not true. And I guess our main result for learning, if everyone is using no regret learning or satisfies the no regret condition, and we use the oldest packets getting served, then interestingly, the very same factor of 2 will work. That is, if I have, so again, the base necessary condition was that for every k, the k arrival rates is less than the top k service rates. And instead, I need a factor of 2 in this condition, and then learning is good enough. And it turns out this band is tight. That is, we can make up examples with particular lambdas and particular mu's, where this is, if this condition fails, the learning is not going to be good enough. So while it's the same band as 2 as what the old paper was about traffic routing, it's a very different style proof. And maybe, while I don't want to give you all the mathematical details of a proof, that's probably not good at this level of a talk, but maybe giving you a sense of how one proves something like this, it's still interesting, or at least I was planning to give you some outline of the proof. So here is the rough idea. It's a potential function argument. And the potential function we're using has a nice meaning to it. It's, but it looks a little bit crazy. So if I take phi tau to mean packets in the system that are h tau or older, and I add this up for all possible taus, that's what makes my potential function. So if the system is good and there aren't any packets that are very old, then phi tau for a big enough tau will be 0, and the other taus will have some value. But indeed, this is a potential function that in some way measures the congestion of the system. It not only measures how many packets we have, but also measures the ages. But it definitely has the property that if we keep this potential function low, or we prove that in expectation this potential function stays low, then we are golden. There couldn't be too many packets in the system. The main tool we're using is a beautiful probability tool by Pimentel and Rosenthal, who proved that any potential function and a random process that satisfies two conditions. One I'm going to come back to, and it's a technical condition about being sufficiently regular. And then the main condition, which is very natural, that when the function phi is large, it should have negative drift. That is, in expectation, it should decrease in expectation. Again, the condition is not that phi always decreases in expectation, only that if phi is very big and there's a band that phi above something, then then it should decrease in expectation. And apparently they proved that this causes it to stay bounded in expectation the whole time. So this is what we're going to prove, and the main proof technique is to claim that the factor of 2 slack that I claimed in the theorem and the no regret condition on the player's behavior causes it to have negative drift. I might give you a hint of what sufficiently regular is, but as you might easily believe, that's a more technical part, and the intuition is behind why is a negative drift. Why is it that when this potential function is big, it's expected to keep going down? So, the simple idea of why no regret helps is I have to remember the one part of this potential function, the number of tau-old packets or tau-older packets. And remember that because of our prioritizing old packets, this set of packets as a group has priority over other packets. So I'm going to think about a reasonable size window of time and say, okay, there one of two things will happen. Either these queues that have the old packets will send to the best servers. And if they do that, then I guess things will actually be better than we didn't even need the factor of 2. Remember, the best servers have enough capacity. So if these old windows constantly send to the best servers, then they will get some extra packets, but more packets will leave the system because the sum of use is bigger than the sum of lambdas. So then we're golden. The potential function, at least this part, the old packets, will decrease. Most of them will get served. If that's not the case, then I want to use the no regret condition. And I guess I want to remind you what the no regret condition is. So remember, the behavioral assumption for no regret was that if there is something that would have given you good service, then you will notice that, or at least do as well as you would have with the single best strategy with hindsight. So in this example, this queue here, for whatever dumb reason, is sending to this bad server. And I guess the assumption says that over time, and I guess now I fixed it with utilities instead of costs, the utility you're getting is not much worse than utility you would have gotten with a single strategy with hindsight. What's the single strategy with hindsight? You should have sent to the better server. If these old queues are not sending to the better server, that means the better server is empty. I guess you could have gone there. You had priority. You would have gotten served. So if you satisfy the no regret condition, then you must be getting this much service someplace else. And while this is,
May I ask a question?
yeah.
Hi. Concerning the, so you hinted at the fact that servers may have some restrictions on the packages that they may be serving, on the clients that they may be serving. Do you know if there are also any conditions regarding perhaps the preferences of the servers, or we don't take care of them?
So not in this. So I guess one way to phrase your question, or I think what you're asking, but correct me if I didn't understand right. One could do a more elaborate model or more interesting model here, where I don't allow every server to use every queue to use every server, but have a bipartite graph between them and say
Exactly,
that,
that's what
your packet can
I,
only go there.
exactly.
At the moment, we don't. I believe actually everything will go through that way, but I admit we didn't work it out. So I have to be honest and say I'm not positive that that will work.
Thanks.
So again, with everyone going everywhere, here is the sort of the way no regret condition kicks in. If they don't go, so the first case was that they all sent to the good servers, and that case they get a lot served. And if they don't do that, then I guess the good servers are empty a lot of the time, and hence they would have gotten good service if they went there, and there must be they're getting this much service someplace else. And this is where the factor of 2 was needed, because I can't assume they always go there, but if they go there at least half of the time, that's the condition 1. If they don't go there half of the time, then half of the time it's empty. So then the regret is very big, and they must be getting good service someplace else. And I guess one thing I definitely swept under the rug, that argument I offered you was particularly focusing on one particular timescale tau. And what I should do is just integrate this argument over all possible taus and to get the potential functions. Beyond the visible technical details, there are a couple other things I swept under the rug. I very heavily counted on expectations. I talked about, if you take a long window and my arrival rate is less than the service rate, then things will go down. I guess I have to be a little bit careful here, because over an infinite time horizon, all kinds of unexpected events will actually happen, no matter how low the probability is. So I have to work with the high probability events. Maybe more importantly, we're actually using a deferred decision version of the model and working with ages instead of packets, and the potential function is actually something a little bit different. This is literally the expected number of packets that are ordered in the system, but expressed in a different way. And I do that because the word sufficiently regular in the condition was that it needs to be that the process needs to have bounded moments, and the actual processes I described to you did not have bounded moments. But if I switch to the deferred decision, like only revealing the oldest queue, then it will become bounded moments, so we can use the theorem. But I'm going to stop here in talking about this result. So again, the theorem was, which maybe I should have repeated on the slide. So I'm going to just pitch back to it, was that, long slide, here it is, that if everyone is a no regret learner or satisfies no regret condition, and we have twice as much capacity as what's needed for a centralized solution, then all queues remain bounded in expectation, uniformly bounded over time in expectation. That is, do not experience a blow up in the queues. You might again conclude or think that you're about to conclude that, hey, this no regret learning is a pretty good idea. After all, it supported the theorem that some amount of extra capacity helps enough. And what I'm going to use in my remaining bit of time is convince you that, well, maybe not. Okay, so let's go back to where we were. That's the end of the proof. And here is the example that I think will instantly convince you that something is weird about this no regret learning. And for this, I have to be actually careful in maybe reminding you how no regret learning algorithms work or what exactly the condition is. But let's start with an example. So here is my example. There are two servers, both have two queues, both have arrival rates a little bit above a half. And I have plenty capacity. This is a perfect server. It always serves something. This one is a little bit less than a half. So remember the condition for existence of the solution was that the sum of the arrival rates or sum of the top k arrival rates should not exceed the top k service rates. That's definitely true. The best arrival rate is only half or a bit more than half the service rate, and the best two arrivals is 1, and I guess this is 1.5. You can also notice that, of course, it does not satisfy the factor of 2 condition. It's not the case that I have twice as much capacity, because twice as much capacity here would actually require me to have the sum of these mu's to be above 2, and it's only 1.5 or less than 1.5. So I don't have enough capacity for the learning result to work. And in fact, as I will prove to you in 1 second, learning doesn't work. Because what they're going to do, both servers, will just always send to the top server. I claim this is it. This is the only solution they can come to. So what happens if they send to the top server? They're going to split the traffic, like, you know, they will age roughly equally, and roughly speaking, they get 50% of the service. And indeed, you know, 50% is not great because slowly they're going to have a queue built up behind them. But if they were to deviate, they're getting a 50% success rate on the top queue. If they go down, it's 47% success rate. So how is that good for them? It's not. So if they deviate, they have regret. And despite, of course, the queues will go linearly, this is not my tight example that the factor of 2 is necessary because the gap here is less than a factor of 2, but certainly an example that, you know, how things can go wrong. There's enough service, there is enough room here, but they're not using it. It will cause linear growth. Okay, this is not so surprising yet. Let me show you the surprise. What would happen if the second, one of them, say the second one, decides that, you know, every now and then, say 10% of the time, I'm going to send to that lesser server, even though it's a lesser server. So I claim that this is actually in English, unfortunately not according to the no regret condition, but in English, it's viewed as a myopic move. It actually helps. So if you look at it up front, it does look like actually he's just being altruistic because, you know, he doesn't always send to the top server. So obviously you have the top queue because 10% of the time he's alone and he can just clear. Instead of 50% service rate, he gets, I don't know what the percentage, but, you know, split some of the 90% and 10% of the time he just goes through anyhow. But as it turns out, he's actually helping himself also, because what really happened here is that because the top queue will queue faster, its packets will be a little bit younger. And that means that whenever the second one goes up to the top one, he gets priority because his packet is older. So what happened is up front, he helped his buddy, but that means his body's packets are younger, and then he gets priority, which means he's actually helping himself. So let me actually try to get this example, help you understand the example. Again, superficially, iteration by iteration, it looks like sending to the lower and lesser ability server causes regret. It's a problem because it has only less than 50% success rate, and on the top queue getting 50% success rate. So how can it be better for you? But it causes an interesting long-term effect, namely that your packets will get a little bit older than the other guy's packets, And as a result, you get priority. So when you go up to the top server, you suddenly don't get 50% success rate, you get a much higher success rate. And in fact, with these numbers, like 90% and 10%, everyone's packets always go through. So in some way, you can say that this is an altruistic move, because what's really happening actually helps the top queue more than it helps the lower queue. That is, the top queue will get its packets through faster. But in some way, it helps both of them because they both get through all the time. It's definitely better for both of them, even for the low queue. And to give you a comparison, what we proved in the learning part of what I told you about is that no-regret algorithms, you need a factor of 2 increase in the capacity. It turns out that if I take it in a different way, use a more patient model, then I don't need quite a factor of 2, but a little bit lesser factor. So instead of 0.5, it's e minus 1 over e, which is 0.63. The numbers are not that different, but as the example illustrates, there's something fundamentally differently happening. And I guess we call this if the servers are evaluating the outcome more patiently, then you need less capacity. So this is a second paper. I'm not going to give you much of a hint on what the proof is, in part because 2 proofs in a single talk is maybe too many proofs, or maybe because of the time. But let me actually try to give you a sense of what is going on here. So there is an awkwardness in what no-regret learning does, both as an algorithm, for those of you who actually know what these algorithms do, and also what the condition is. And this is because our notation for no-regret learning didn't actually take into account the long-term effects, carried over effects between iterations. Instead of what I used to have here, that cost of iteration I of the actions you took at time t, what I really should write is cost all the actions you took from the beginning, because there's carryover effect. What happens in iteration I, iteration t doesn't only depend on what you do in iteration d, it depends on the whole history. So a better notation for our perspective would have been something like this: for over time t, cost for the player I on what happens for him at iteration t, given what all the actions were for everyone all the way to iteration t. And then the single action comparator turns out to, in this notation, come out to be a little bit weird item. That is the cost of what would happen if on iteration t, he switches to this fixed action x. And this is how the algorithms really even work. What no-regret algorithms do is what in learning often called explore exploit. That is, try things, and if it works well, they stick to it. And that's the explore. The try things is the explore, and exploit is that if you figured out what learns, then you do that thing. And that's what this notation wants to say. That is, what you're doing is, had you did this new action x, everything else stayed the same for up to iteration t minus 1, but up to iteration t, you did this x, where everyone else is doing the same thing, and what is your cost is no bigger than that. But that's not what we mean in a game with carryover effect. What we really want is this. What would have happened had you sticked with x all the time from the beginning? So this says you experimented with x on iteration t. This says you have been doing x all along. And this is what we really mean. And that's not what the no-regret condition does, and that's not what no-regret algorithms do. And it's not even clear what is the algorithm that can achieve something like this. So it's not clear how to play with this. What we do in the paper is actually switch back to, instead of studying learning, because I said I don't know quite how to do this, look at equilibrium conditions only, and we proved that 0.6663 theorem on the equilibrium condition. And I guess I'm going to maybe flip through the slides of the hints of the proof, but I guess what is the theorem says that if every player fixes a fixed randomization over servers, and then if that is a Nash equilibrium of this game that induces a Markov chain of how the Q ages evolve. And we look at the asymptotic aging rate, which they're trying to minimize, and look at that game and then prove the theorem that, or at least this result is about the last item here, Nash equilibria of this game. Again, I will not show you the proof, which admittedly is maybe a bit more complicated than the learning proof, but maybe useful to just show two examples. Like, for example, here are 4 servers and 3 perfect, 4 queues and 3 perfect servers. This is, for example, a natural Nash equilibrium, and in fact, a very good Nash equilibrium, which works perfectly. As long as these arrival rates are below 3/4, everyone gets served. And this is a perfect system. In contrast, the very same system, there's a different Nash equilibrium that's much less good. Here's what it looks like here, or somewhat less good. Here, I have to have the arrival rate below 7.3, so 0.73, so lesser. And I guess one thing that went wrong here, which is maybe despite that this is a Nash equilibrium, on this particular server, they're not using the full capacity. Because they independently randomize, they sometimes don't send here, and that's a wasted capacity. And really what we need to analyze is how much wasted capacity happening. Elsewhere, our worst example, and in fact, the tightness of the band is coming from a very natural place, namely the Nash equilibrium, where every one of these queues is uniformly randomizes between the servers. Because this is such a damn symmetric solution, you can believe me that this is, of course, a Nash equilibrium. What else can they do? It's so damn symmetric. And as you know from Bose and Bin's analysis, a 1/e fraction of the servers becomes unused, and it's wasted capacity because they leaving it empty, which they shouldn't have. So I guess I don't know. I think it's given the time and maybe again the interest, it is best not to just flip through the proofs and not actually show you any details of the proofs. Maybe I was too optimistic in being able to show any of this, and just end with some summary of what I'm hoping the take-home message is and what you might be interested in. So I think there is I think learning is still an incredibly good model, even if I'm less sure of what is the right model, what does it mean to learn. In all of these systems, in reality, there is some learning happening. They might be not using the actual no-regret learning algorithms. They use gradient descent or all kinds of standard sort of continuous algorithms, but players do use learning to figure out what to do, and it would be nice to model what's happening there. We don't have any good understanding of what's happening with price of energy results with learners in a repeated game that has carryover effect, and a lot of the games in life have carryover effect. So we have now 2 sets of results, one in no-regret learning, and one is in a super restricted version of the game, and one is an equilibrium. One big question is, this is a pretty simplified game of either packet routing, and one wonders what else this kind of result carry over. I would like to have a more general routing game. And of course, we all would like to have budgets and auctions. If you think of how online auctions work, that is a repeated game with a carryover effect, because when I spend my money, I have less money left. That's a standard, like equally powerful carryover effect. If I lose the auction, I have more money in my pocket. If I win, I have less money in my pocket. That's a carryover effect, not about learning, but about cash in my pocket. And then I guess the question I more emphasized, and that's the one I'm going to end with, is no-regret learning is as an algorithm or even as a paradigm too myopic, and is there a better way of patient learners, or is there a better model of what learning means when we take into account that the learners might be realizing that to see the effect of what they're doing, they need to be less myopic than the no regret condition assumes. And I'm going to end here, and thank you for listening.
Thank you very much. We have time for questions now. Please ask them in the chat or unmute yourself and go ahead and ask them.
So maybe, Eva, if I understand correctly, so the no regret is not working well for, I mean, you can do better with for carryover games, but the situation is it, so when you say that you don't know, means that you don't have an algorithm for actually improving on this, you have only a special case in which you know what to do. Am I correct?
We have a theorem that if a Nash equilibrium of this game, or a patient Nash equilibrium, when they do take into account the long-term effect and they reach an equilibrium, which I have no idea. I mean, I proved that equilibrium exists, but I don't have an algorithm to help them reach the equilibrium. Yes. So that's not a fair condition, but it's the classical price of energy analysis. If they were to reach a Nash equilibrium, we need less capacity. What I don't have is, I don't have a proposal or a viable proposal, not just an algorithm that will reach this, but even a condition. What might be the right condition for learning? So, I guess.
So
I gave this talk at EC, or actually my student, Jason gave this talk in EC, and at that point we had a proposal for the condition, but there is a recent paper with some people, including Vinay Parchet, who showed that our guess was wrong. So I can tell you what the guess was, because it I think is in the right direction, even if technically it's wrong. There is a better version of what no regret should mean, actually originally proposed in a very different context of thinking about games where cooperation might help, is that you shouldn't just, I guess the example they used to like is prisoner's dilemma. And prisoner's dilemma, as you know, the only no regret condition is to defect all the time, because the no regret condition is stupid enough to realize that had I cooperated, maybe you would have cooperated with me too, and we would have been all better off. That's not in the no regret way of thinking. The no regret way of thinking just says, given what you, Andrea, was doing, I was always better off defecting, and not taking into account that you're going to react to this. So there is a version of learning that they propose or study in such cooperative repeated games. And I guess originally I was proposing that, okay, that's the condition. They actually have algorithms that achieve it. That is the condition I want. It's not because of cooperation, but because something similar is happening here. Cooperation is a long-term effect. If I cooperate, that might induce you to cooperate. That's a long-term effect. And here we have a different long-term effect. But unfortunately, Vinay's paper proves that technically that condition is not good enough. So I need to think about, but I think something like this is what we need. Some a learning that remembers that you have to wait a bit. You don't just try X and then back off like explore exploit does, but try X and stick with it for a while and see what the effect is. And it might, and in that one example, it will instantly, if you wait a bit, it will have a good effect. If you try it instantly, it looks bad, but if you wait a bit, it will show its good effect. And so I think something like this is the condition we're looking for. These are algorithmically doable. I just don't yet know what is the strong enough condition that I can mathematically prove to use it.
Yeah, makes sense. So this example about the 90% and 10% gives some impression of a randomized strategy could work.
Yeah, that's another fact. They need randomized strategies. There's no deterministic answer there, right? Because if you go down to the bad server, that's bad server, you're not going to succeed. If you stay at the good server, then you're competing, you won't succeed there either. You have to randomize. And in fact, one technical difficulty for the learners is that this is not a convex space. Like in the discrete version, we know that the deterministic strategies are best because the randomized one are just convex combination of the deterministic one. That's not true here. The optimal strategy is in the middle. But you know, there are learning algorithms that can handle this. I think my problem is not that I don't have an algorithm for the learner. I don't know what condition I'm hoping that they reach. And I used to think I know it, I just don't see the proof, but given the new paper, I now know that that wasn't quite the right condition. But I think something along those lines is what would work. And these things are reachable algorithmically. And they're very natural, equally natural. Instead of trying this X, like you should just be more sticky in your explore strategy. Like instead of trying X once, you should try it for a bit, watch its effect, and then, then back off.
Yeah, but this watch, yeah, I can see your point. But how much you have to stick with the strategy, that becomes the question, right?
So again, the condition that I know is reachable, they do this exponential increase, like they try it for 1 iteration, 2 iteration, 4 iteration, and they cycle around, and then they kind of have a band of if some number of iterations was beneficial, then in time, twice as much or something, you're going to reach trying it for that long, and you're going to discover it.
Yes.
Again, these are all theory results. So if I lost a factor of 2, then, well, true. Especially the time to convergence, I'm willing to lose factors of 2s.
Thank you.
Thank you for the question and for the answer. Does anyone else wants to ask something or comment? If not, let's thank the speaker again. Thank you very much for this very interesting talk.
Thank you guys for coming.
Thank you
and hopefully,
for having delayed the second talk.
Yeah, hopefully one of these days I can actually visit Montreal again. It's a nice, yes. It's a nice city.
Yes.
Maybe